So we do need to copy what's in the DRAM into persistent memory. We also flush what's in the CPU cache into persistent memory and capture them. And that's part of our checkpointing or snapshot mechanism. And so that will be, we make sure the entire application state is persisted.
Okay, great.
All right.
Thank you, Charles. Appreciate it. So we've gone through the hardware and software elements of big memory. Let's up level a little bit and move on to some system side view of big memory. And next up will be Kevin Tubbs, Senior VP with Penguin Computing, to take us through the next session. Kevin?
Thanks a lot, Mark. Yeah, my name is Kevin Tubbs. I'm the Senior Vice President of the Strategic Solutions Group at Penguin Computing. I'm excited today to talk to you about LiveData, which is a solution that Penguin partnered with Memverge and Intel have been working on over the past year and a half, but it's designed for when data is greater than memory. Gonna give this a little bit chance to catch up. I'm gonna go into the agenda for today, where we're basically going to talk about how Penguin does the research and the development, and with our partners to get this technology out to early adopters. So we're going to talk about the data practice in our innovation lab. We're going to talk a little bit more about our LiveData Solution at Penguin Computing, and kind of go into some use cases. And I think we will reiterate a lot of things you heard today about the core hardware technology that's driving this. And what that actually does is present a level of platform complexity that's driving it harder with other emerging technologies to deliver an actual benefit back to the customer. So that's where we're trying to lead on the cutting edge there. And also, we'll also talk about some of the trends that we're seeing in the market, similar to what Charles mentioned, where we do believe that in addition to the hardware complexity, we see a retreat of users to the user space and focusing on the workloads. How do I make sure that my data-centric and more specifically memory-centric workloads can be optimized so I can advance my business and technology objectives and get time to insight faster? And definitely one of the trends we've all been seeing in the market is everything, even HPC, as well as traditionally high performance data analytics and AI are becoming more data driven. So inside our data technology practice, we look at how do we deliver complete solutions. And I'll go into more detail of what we think a complete architectural model for a solution should be. But how do we look at the data problems and deliver something that gets you to that time to insight faster? So today we'll be talking about LiveData, and that's how we deliver powerful, validated, flexible big memory so you can adopt it faster. Active data is more how do you look at this, the full data hierarchy, high performance storage that Charles mentioned, all the way through deep data. That's our capacity solution. And we also think about how to have that data portability between different locations as well as different clouds. So all of this becomes very important to deliver in a complete solution. So the key thing is here we look for how to deliver a workload optimized platform. And as we go through that, you'll see that everything is dependent on the use case, dependent on the application, depending on the workload. And that changes a lot of times throughout a whole pipeline. So having that agility and flexibility to deliver the right solution kind of lands to where you always are going to need a software-defined architecture. And that's why the combination of the hardware from Intel and the software from Memverge allows us to have that software-defined architecture which delivers flexibility. So now I'll get into LiveData. So as we talked about earlier, I won't spend too much time here. Andre did a great job of talking about the core technology, but we're just looking basically at, what are the difference between DRAM and persistent memory? Large differences are the capacities that are available to us. From DRAM going from 16 to 128 gig, DIMMs to persistent memory, Optane persistent memory from 128 to 512. So in here you have different capacities, we have different latencies and performance, but we also have inherent to that different costs. And those are the key things that we need to be able to understand to apply the intelligent placement of the NAND technology into a platform that allows us to deliver a complete solution. So I'll start looking at some of the obstacles facing the adoption, or what we see as the adoption of persistent memory. And one common point people look at, well, persistent memory isn't as fast as DRAM. And as Andre talked about the entire data hierarchy, there is a gap here, but the perception that DRAM, that persistent memory isn't as fast is true at its bare nature, but it's how you use that together that allows us to overcome those obstacles. Another one here, why not get a larger server that supports a larger DRAM capacity? That is an approach to do to meet memory-centric workloads, but we question whether or not that's the only approach. So do I do that by having more memory DIMMs, more memory capacity? But that still is going to give me a level of volatility that is just memory or DRAM, and there's also a cost factor there. Another obstacle, memory itself is not highly available. It does not have the capability of having data services on top. And if you do want to develop them, there's some level of application development there. So in cases where you can do that, that's great. But how do I take an application, a new workload that's changing very fast, and adopt that quickly? And the last obstacle we see is this broad adoption. And that means that every application out there that I want to see and take advantage of persistent memory, I have to make sure that it's ported. I have to code it. If I'm doing in-house, I may have that capability, but it also requires software development resources. If I'm using an ISV set of software, I have to wait for them to develop that. So all these things tend to be obstacles that face the adoption of persistent memory. But we believe the concept of software-defined architectures and some of the things that Charles mentioned earlier will allow us to get to that adoption faster. So now I'll go into kind of summarizing some of the things Andre talked about earlier, persistent memory mode options. So we have memory mode and app direct. And we talked about some of the pros and cons of both, with Andre went over earlier, and also how much level of effort is involved. And with most things, the more level of effort involved, the more you can actually get out of it. So as Andre said earlier, you actually do want to get to the point that you're using app direct mode and trying to extract the most performance and the most services and data service out of it, but it does take a level of effort. So it requires a rewrite to be byte addressable in app direct mode. In memory mode, that is the quickest way to use it and gain the effects of higher capacities, but at the end of the day, it's still volatile like DRAM. So memory mode gives up the persistent nature of Optane memory, and app direct requires rewriting of the code. Both are just obstacles and challenges. So what we get by incorporating Memverge memory machine is introducing the things that Charles mentioned in the software, creating that virtualization layer that now allows you to level up from the hardware a little bit, or abstract up from the hardware, and deliver a platform that is plug and play compatible for the byte addressable DRAM mode. Performance, we've seen some of the cases that Charles shown, and I'll show some later, that delivering fast hybrid memory, this combination of DRAM and persistent memory, actually is beneficial to some workloads. Ability to leverage the persistence. So now I'm going to make sure that I don't have to choose which way I want to use the underlying hardware and technology. I have the flexibility to take advantage of the persistence. And to Charles' points earlier, now I can add data services on top of a growing area of need and workloads in the memory-centric computing, but now add data services like zero IO snapshots, cloning, and in the future replication. So that's kind of the combination of where we believe adding a software-defined architecture gives you the flexibility to meet the dynamic and changing needs of your workloads, but also to accelerate your time to adoption and accelerate your time to insight. So I won't go into this a little bit more. Charles talked about it. This is why we're all here. This is why we're all excited about it. The growth of this market, we're going to see grow. And as these technologies build and this ecosystem build, it allows us to deliver a complete solution faster, and which will allow us to change some of the landscape of the workloads that we're delivering. So now I'll get a little bit more into why we partnered with Intel and Memverge to create our LiveData Solution, which is a platform in itself, which we want to deliver a complete end-to-end solution, a complete turnkey solution that allows us to listen to a customer's specific workload needs and challenges, choose a platform that's vetted, tested by all three of us actually, Penguin, Intel, and Memverge, and allow the market to know that this is a valid platform that which you can build your workloads and applications on top of. Key features here, tiering between the memory and the DRAM. So not having to make that choice, but actually able to level it, leverage both of them efficiently, and then dynamically across workloads. We'll go into some more details about the features and benefits as we get into the use cases.
So Kevin, this is Mark. I'm going to jump in here. We did get started in your section a little bit late, but I do want to be sure we have spend time on the use cases, HPC workloads and use cases. So just with that in mind, just kind of a time check here. Thanks.
Okay, sounds like a plan. So here, I think this is a good one to leverage it, lead into the use cases. So here at any, we have what we call for our LiveData architectural model or our process. We're looking at how to enable users, what workloads are you running, AI, ML, real-time analytics, even cloud and VDI workloads. Understanding what software technology, so what orchestration, what schedulers, be it HPC or Kubernetes, what type of compute that you're leveraging on, leveraging what type of data technologies, and then at the end of the day, what data center component, how do you scale this out? And on the example on the right, these are traditional EIA servers and how to scale that out efficiently. So this just shows the overall process of how to solve a problem with live data. And then here again, we're summarizing what we talked about earlier. The goal is apply Memverge to be able to give you a single hot tier that leverages and efficiently uses both DRAM and the capacity of Intel persistent memory. In the interest of time, we've already talked about this a lot, but use all of the memory capacity, different flexible DRAM to persistent memory ratios, and different HA capabilities. And I won't labor on here, but the goal here is that you have different building blocks, some for high performance data analytics, some for dense HPC, which is traditional 2U4 node, and then different variations with GPUs or other accelerators. But here it's how do I build the building blocks to deliver at scale? And you'll have the slides to be able to look into this more details. How do you deliver it at hyper or sub hyperscale with open compute platform? So we have the capability to vet and test all of these things. So as we get into the use cases, all of these were tested on the previous platforms. So what do you look for when you're trying to understand which use cases to target? Mark talked about a little bit earlier, which verticals, but really we're looking at real-time workloads, anything that's latency sensitive. So we get a lot of interest in transactional workloads, trading, economics, things like that. Real-time data analytics, anything with high ingest rate, high data analysis, where you're either operating and generating data fast. And then Charles went over some with the AI and ML. So these are some of the real-time workloads as you look for low-hanging fruit. We are also working with Memverge and Intel to start testing out a lot of the traditional HPC workloads in life sciences as well as manufacturing. So I'll go over some of these, just an example. We're looking at in-memory databases that, based on the original technology, you're limited to, from a TCO perspective, small amount of memory per server, but then having to scale that out over a distributed in-memory database across 40 servers. So that allows you to get the performance you need for memory. But one of the key problems that jump out of that is what happens when I have a crash? What happens when something goes offline? And the problem here was, on this specific use case, and not having a persistent memory, it takes 24 hours to restore from a crash. So it's not only just the performance, but it's the productivity of the overall environment. One key here would be, instead of using just DRAM, go over to persistent memory by itself. And at that point, you can deploy a lower cost persistent memory, but the objection there is, I'm going to sacrifice performance. So as we go through the solution using Memverge, we actually are able to leverage both and allow for the Hazelcast cluster to restore in seconds. So you move from 24 hours down to being able to restore in seconds. And we also have a TCO where the persistent memory provides twice the memory for the same cost. Also in that, you have a native redesign of the environment, and there was able to have a 10x server consolidation. So here, we're allowing the redesign of the cluster to increase productivity, also save money through the TCO, save data center space. And then the technology inside of Memverge allows you to use that application without having to rewrite or recode. And in this case, the technology allows the combination of persistent memory and DRAM to go as fast or faster than DRAM. So this was a financial high performance computing case. We have another case, financial services, where we're looking at AI and ML inferencing. And this just shows that we're looking at, this is transactions per second. And it just shows how, as we look and go through using DRAM as the baseline, how do I change flexibly the ratio of persistent memory and DRAM that's used by the application to understand how to optimize it. And in that case, from here, I'll just highlight that we found a case where persistent memory plus 16 gigs of DRAM ended up being 3.5% faster than DRAM itself. And what you get out of that for this specific data size and use case is equal or better performance at a lower TCO. And then another use case for us, we're moving on, is big memory for media and entertainment. So in this case, we're understanding that for an artist to be able to access and do the work that they need, it needs to be at memory speed. So they're always looking for larger RAM, larger ability to continue to work faster. But again, similar to what we talked about earlier, productivity is important. So if an artist loses 16 hours per week, or 800 artists lose 16 hours per week, based on they generally lose 1 to 2 hours of productivity per week by a system crashing, we're able to find a way to save 83,000 hours of creative artist time lost per year. And this is done by, one, using it inside of a workstation or a remote desktop workstation, which also increases productivity, and then allowing them to work on larger data sets at a lower TCO, but also recover from that snapshot faster. So when we look at the solution, of course, is to apply Memverge and lower the TCO of the workstation, but also you'll see that we're going to be able to enable a capability that they didn't have before, and that's to auto-save the actual environment. And it has a large potential savings annually based on the combination of TCO and also artist time. And also the goal is to deliver higher quality movies and be faster time to market. So if we look at that kind of more details, before they would snapshot this every few hours because it's very disruptive to the workflow. And it's a manual snapshot. The snapshot itself would take minutes. So we're taking 10 minutes. The restore, if I did have it, would take even longer, and it's going to take hours. So we're looking at 3 hours. By applying the Memverge and LiveData Solution into a workstation environment for media entertainment, now I can automatically and auto save every few minutes because it's zero IO, it's not disruptive. And then my snapshot now takes 1 to 2 seconds, and my restore now takes 1 to 2 seconds. And summarizing that, I mean, that's a dramatic reduction in snapshot time and restore time, which ultimately increases the productivity. All right, so again here, I think this is one that we talked about earlier, but this is again, the problem is when data is greater than memory, you're going to see a dramatic slowdown of the AI and ML production inferencing. And then it also takes longer to load and restart, similar to the M&E. So you think about online production inferencing, if you need to have a crash to the system or roll back a different iterative model, then you're able to do this more efficiently. So the solution here, use Memverge to create memory lakes that combine both the DRAM and persistent memory and add data services on top. And in doing so, we were able to, this is just a smaller subset of what Charles presented earlier, you're able to see what I can do when everything fits in DRAM, you know, my inferencing model, total inferencing time, 234 seconds. When I go beyond what's in memory, that jumps drastically to the end to using NVMe for swap. We look at 2 use cases using LiveData where I can use DRAM and persistent memory, or all persistent memory. And using DRAM and persistent memory, I am only slightly slower than DRAM on itself. But the other thing, or other vector that you have here, is by allowing me to be able to use or not have to slow down when data is greater than memory, it also allows me to understand how I do a building block for multiple and scale out multiple production AI and ML inferencing. So I can now run more models. I can run more flexibility by putting the embedded tables that Charles mentioned earlier into persistent memory and running the models into DRAM, and having this flexibility allows me to increase the speed and overall throughput through the entire cluster. So I'll stop there. At the end of the day, what we're trying to do here is reduce the amount of time to adoption of these technologies by having a completely vetted and end-to-end solution. And we've talked to a lot of customers, and we're seeing their ability to take their workloads, put them into a big memory production system, test, validate, optimize that workload a lot faster. So I'll stop here and see if we have any questions.
Great, Kevin. Thank you so much. I think the systems perspective and looking specifically at some of the HPC use cases and how they can benefit from the technology is extremely helpful and useful. It does look like one question did just come in on the Q&A window.
Do all the performance comparisons assume that the entire data fits within DRAM and persistent memory, i.e. no storage required at all? So in this case, this was a subset of the use case that Charles had. And then I think we have another paper that's, even more exhaustive. But in the cases that we're showing, the model and its embedded data were able to fit inside of DRAM and persistent memory. And then when we increase the number of models going through that server, or we increase the size, that's two different ways that we consume more data than DRAM. And then that's what we were comparing with no NVMe. And then all the other cases are still limited to what does fit in DRAM and persistent memory. And we're looking at the different server configs and scale out configs and how they scale out to achieve the overall online inferencing production design, if that makes sense.